Okay, questions? No questions? Okay, well, one thing, we had an exam next week, right, next Friday. So everybody started to prepare for that, right? I won't ask for hands. But what are you going to need to know? Everything, or a good chunk of everything. So, somebody asked the other day in the other class, well, are you going to give us a list of reactions? And I said, why would I do that? Which apparently was sort of a snotty answer. But it's been a snotty week, so. One of the things that, in order to prepare for the exam is to go through the reactions. You're going to need to know your reactions. And you're going to need to know them fairly well. You're not only going to have to write the products, but you might need to know the reagents. If I give you reactant, product, and you need to tell me what the reagent would be. So one of the things that I might suggest is, let's say you could make 3x5 cards, where on the front you might have something like, if we were looking at alkyne reactions, we might say, okay, that alkyne plus H2O plus H plus H2O, and so I'd put that on the front of the card. So that as I'm flipping through it, I would then be able to write down the product. I would suggest on the back, you might put the answer, but then go directly from the reactant to the product. So that way, when you have your stack of 3x5 cards, and if you do this for all the reactions we've talked about this semester, along with the alkene reactions from last semester in SN1 and SN2, your stack of cards is going to be, it's going to be a couple inches. Then you could flip through the front side to write the products, and then flip over and remember the reagents. Because if you look at the older exams, there's bits of each one of those on the exam. So my suggestion is that if you feel like you're kind of like, I don't really know this stuff, this is a first step, because you have to know your reactions. You have to be able to write the products. You've got to be able to give me the reagents that you would use for that. Okay, and if you want to do it on sheets of paper, that's fine. If you're into 3x5 cards, if you want to put it on the computer with whatever Quizlet, or there's another one that a medical school student was raving about to me a couple months ago. It's something on the Mac. Whatever. But as you put the time in to assemble this, it's going to help you in terms of remembering it. So I could give you the list of reactions. But what I'm going to do is the same thing you would do, which is go back through the notes, see the reactions I've given in the lectures, the ones we've talked about in class, and the ones that are like in the homework problems. And I can do that, but I already got my grade in organic. And surprisingly, it was good. Wasn't spectroscopy where I didn't do well. And then decided to do that in research for nearly the rest of my life. But you have to invest the time to do that. Now, mechanisms. If you look at the older exams, you're going to see what you're going to see next Friday. Right? At this point, I'm not very creative. Creativity takes energy and ambition, and I'm short on those right now. That may change next week, but not right at the moment. So you're going to be asked to write mechanisms. What mechanisms? Any of the mechanisms we've done in class, any of them that were in the notes, the lecture videos, etc. So all of the reactions of alkynes, particularly like this one, where I'm forming the ketone, you'll see that on a lot of old exams because it's got the tautomerization in it and everything else. So as you're, those I don't think are 3x5 card worthy. I think those are probably something you would put on a piece of paper and practice. The older exams you can practice with. Last year's exam has alkynes. It has the same materials this year. If you go back, I think 2 to 5 years, you're not going to see alkynes because it was in the first semester. But that's okay. You could go to the first, well, actually you can't because it was on the final exam. So if you go back like 7, 8, 9 years, in those exams, you're going to see triple bond reactions to use again as practice. So all I can say is that you want to begin to get these reactions in your head. And so whatever method you want to use, whether you want to use 3x5 cards, whether you want to put them on pieces of paper, whether you just want to randomly remember them, whatever works, you've got to do that. Okay. So that's my suggestion if you feel like, I don't know where to start. Well, you might not know where to start because you need to remember what kinds of reactions we have. Okay. And it's always dicey when I give this kind of advice because then some people are like, "You want us to fail. You're saying this, you're in the tone you're saying it. You want us to fail." But trust me, if I could grade every exam and it's 100%. And I only have to spend an hour on total grading, that would be great. Of course, that's all about me, not you. But honestly, at this point, we're going to be going through how many reactions every day, it seems like. So you need to get those under control in whatever method you use. And if you don't invest the time in it, you're not going to know them. So that's what I would suggest if you feel like you're kind of lost in terms of like you looked at this one and said, I don't know what the product is. That's the one I'd start with first. And it may seem overwhelming, but it's like one of the students who had to run like 100 samples through the instrument said the other. I said, well, you got to eat the elephant one bite at a time. And the only way you finish is to start. Right? Sorry, I don't have any of Dr. Chai's, great wisdom. But that's how you have to start. And so you just have to plug along at it. Okay. So before you start looking at practice problems, you may want to get your reactions down. And the best way to do that is to, go back through your notes and start putting them together. And if you feel like you could send me a picture of them and say, hey, does this look like something that might be useful? I can tell you yes or no, but again, it's ultimately what your system is. So if you haven't started a system, it would be helpful to try and do that to prepare for next week's exam. Okay. All right. Because if you look at the older exams, it's going to be mechanisms, it's going to be reactions, and then whatever other questions I come up with. Lexi.
Is there going to be stuff from I was going to ask if there's going to be stuff from the review quiz or anything else.
Not all of it, but the stuff that's relevant. So what I would say, for instance, is alkene reactions were very much like the alkyne reactions were very much like alkene reactions. So you kind of need to know those, because when we did the first step, we made an alkene, and then the second step. So you kind of need to know that. But like R&S configurations, I'm not going to just pull an R&S configuration out. So not everything, but a lot of it, maybe. Particularly given the kind of stuff that was today was a lot of review. It was really rooted in review from last semester, so we'll go through that. Melanie? Chapter 15, probably the stuff we do today, and then maybe what we do Monday. Depending. If it's kind of review stuff, then yes. And today's stuff it's review when it's new, but it's yes. Today's yes. Okay. All right. Then questions about the stuff from today. And I handed out some problems if you didn't get the problems. So the reactions of alcohols that basically make up the end of the chapter here. Or actually, we're not quite done with the chapter yet. But some of these reactions of alcohols we have seen. So, for instance, let's look at question number. Let's look at C to begin with. So, question C is. So let's start with that one. What would the product of that reaction be? Or let's say you didn't know. How would you work through that? Okay, I've got an alcohol plus H plus and Cl minus. If this was a mechanisms question, what would the first step be? Protonate the oxygen. So let's protonate the oxygen. Next step.
Have the chlorine attached to the
Like that. Are you sure? Does the water leave first? I mean, could I have the water leave and then the chlorine attack the carbocation?
It depends if it's SN1 or SN2.
That'll make it SN1 or SN2. So if I have the water leave and get a carbocation, that'll be SN1. This would be SN2.
It would be a primary carbocation.
So in this case, if the water was to leave, I'd form a primary carbocation. Right? If I had the water leave, then I would end up with this primary carbocation, and is that stable? No. So in this case, the water cannot leave. What if the system was secondary or tertiary? Then the water would leave. So in this case, that cannot happen. So then my chlorine's going to come in and kick off my water. So if this was a mechanisms question, and I said write the transition state, what would the transition state look like? It would look like that, right? Because I'm doing an SN2 mechanism, so I would see the SN2 trigonal bipyramidal transition state for this reaction. What am I missing in this transition state?
Partial charging.
So I need the partial charge of the chlorine. Partial charge on the oxygen. Delta plus. So that would form the final product. So that's an SN2 mechanism that we kind of did last semester as well. But now that we're talking about alcohols, this is a reaction of an alcohol to do substitution of the OH with the Cl. And so I'm going to substitute the OH with the Cl by adding acid. I could even go back and say, remember last semester how we in lab took our alcohol and we added sulfuric acid to it along with some bromide, and we made the butyl bromide? Right? That's how much of a review it was from last semester that we even did it in lab. So when we have alcohols, we can either do them with SN1 or SN2. The issue is that if I'm going to try and replace the OH with a Cl or a Br, I need acid first because I've got to protonate the OH, because it'll leave as water. It will not leave on its own. Hydroxide is a strong base and a terrible leaving group. So I need to protonate the OH first. And then if I get a carbocation, I can always have all the rearrangements.
So the one with rearrangement would the primary carbocation form and then it'll switch over to be a secondary?
No. No primary carbocations. So if I asked you to do this reaction with rearrangement, we would have to do this. I would still protonate my OH to form my oxonium ion. That's always going to be the first step. But now what I need to do is now I need to rearrange the molecule without ever forming a primary carbocation. So what would happen is we would have a hydride shift so that the hydrogen would shift over here and kick the water off at the same time. And so once that happens, once we get that hydride shift or carbocation rearrangement, once the hydride moves and the water leaves, we would end up now with the hydrogen on the primary carbon and the tertiary carbocation. And then your chloride would come in and add to that. So that's how we do the shifts without ever forming the primary carbocation. Questions? So, in the material for today, there is some new stuff. And the bulk of the new stuff is to basically say, to have a problem like this. If I said, give me a reagent to do that, to form that double bond. What reagent would I use?
H2SO4.
And
H3PO4.
H2SO4 or H3PO4 and
Is it H plus?
they're the source of H+. And, Katie, heat, the triangle. So if you want to do this reaction, you need H2SO4 or H3PO4, phosphoric or sulfuric acid, and heat. And that's what the little triangle stands for. So this was what we called a dehydration reaction. And dehydration reactions can go by either an E1 or an E2 mechanism, depending on whether or not they form a carbocation. So in this case, H3PO4, H2SO4 are acid, H+. First step in the mechanism.
Rotate the oxygen.
Right, we could have all said that in unison. Protonate the oxygen. Okay? And hopefully everybody was sitting there in their own mind going, protonate the oxygen. And hopefully you're like, I'm getting tired of hearing that. Good. because we do that so much of the time. And I'm kind of big on those little tedious phrases. Learned high school math that way. High school math teacher was like always going around calling on people in class, which today would cause traumatic psychological damage. But he'd always, what's the definition of this? What's the definition of that? And just to avoid embarrassment, you had to learn it. And in the end, you knew it. So, right? I am not just randomly, I'm just not pointing at people, but I could do that. So we're protonating the oxygen. Okay, what happens next? It's almost like the last problem. What happens next?
Water leaves.
Water leaves this time. Why? Because if my water leaves, I form a secondary carbocation. I form a stable carbocation. Okay. And what happens in the last step?
Beta hydrogen gets removed from the double bond.
I'm going to lose a beta hydrogen as an H plus to form the double bond. I got two beta hydrogens here. Beta hydrogen A and beta hydrogen B. Which one should I lose? You don't even have to raise your hand, just shout it out. I heard 3 A's.
A.
Everybody want to go for A? Anybody want to go for B? Why did we choose A?
It'll form the most stable.
It'll form the most stable double bond, most substituted double bond. So if I lose my H, A plus, then I'm going to form the most substituted, the most stable double bond. So then I have one more question. What is the mechanism then of this reaction? E Come on, E1. No, it's good you're yelling out the answer, but if it's not the right answer, I'm not going to accept it. So it's E1. Why? Because one mechanisms have carbocations. So in this case, the fact that I formed the carbocation means this is an E1. What is the major product of every E1 reaction? The most substituted. Whose rule is that? Zaitsev's rule. So whenever you form a carbocation, you will always get the most stable double bond. That's Zaitsev's rule. Okay. Oops, where did that come from? So H2SO4, H3PO4, we use as acids because what's going to happen is they protonate the OH. And then if the OH can leave, you form the carbocation. But the problem is, this is why I don't go into this mode. If I end up with an HSO4 minus as my conjugate base, once I lose the H plus off the H2SO4, HSO4 minus is a lousy nucleophile because it's stabilized by conjugation. And so it will not attack the carbocation. If I tried to do this with HCl, as soon as I form the carbocation, the Cl minus would come in and add to the carbocation. So H3PO4, H2SO4, lousy nucleophiles as their conjugate bases, and so they are used specifically for dehydration. And most of the dehydrations go by E1. And E1 mechanisms always give the most substituted double bond. So in this case, that's how I would make this double bond from that alcohol. But now I want to throw a wrinkle on that. If everybody's okay with that, let me throw a wrinkle on this. That's not the double bond I want to make. Let me get the blank slides there. I want to turn this alcohol not into the most substituted double bond, but I want to form the least substituted double bond. And to answer this question basically is what the entire set of material is about. So what reagent would I use to do this? I want to form the least substituted double bond. So what reagent can I use? Ashton?
Would it have to be something similar to turpentine?
I like the caveat of something similar to tertiary butoxide. Why not tertiary butoxide itself? We agree? Carolyn?
Well, would it be like the twaddle ester too?
Maybe. Actually, I'm going to need to use the tosyl ester or something else. So somebody had to fall right into the trap and say tertiary butoxide. Because when we think about making the least substituted, what do we think about? Tertiary butoxide. But last semester when we talked about tertiary butoxide, it was tertiary butoxide with what kind of molecule? An alkyl halide, not an alcohol. So yes, we need the tertiary butoxide, but not as a first step. Because what does tertiary butoxide do with the OH? It's going to deprotonate it. There's going to be an equilibrium between this deprotonating that OH. They're both basically an alkoxide deprotonating an alcohol. It's going to be an equilibrium reaction, but that's what the tertiary butoxide is going to do, is go after the alcohol. It's going to deprotonate it. It's not going to do E2. It will do E2 if it's an alkyl halide. Okay. So this, basically answering this question, takes us down the road of the tosyl chlorides, of the PCl3, of the HCl, of all of those reagents. All the material that was in today's, all those reactions can be thought of as ways to solve this problem. I can make the most substituted double bond from an alcohol using sulfuric and phosphoric acid all day long. What if I want to make the least substituted? I've got to change the alcohol into something else. All right? Let's change it into a chloride and then add tertiary tertiary butoxide to it and form the less substituted double bond. Is that a good scheme? Yeah. How do I convert the alcohol to Cl?
And HCl.
HCl? You don't like that? Why not?
I forget what specifically the book said that it does, but something about it didn't work, and it only worked for bromine. Iodine.
Oh, okay, so you don't like HCl, you want HBr, and we'll convert this to a Br. Is that better?
Trying to find the part.
There are disadvantages. There are disadvantages of trying to add HCl to the alcohol. I can think of a couple of them. Like, what did we just deal with in the last problems? The idea that if I added HCl, I would protonate the OH, the water would leave, I'd get a carbocation. What could that carbocation do? Rearrange. So HCl or HBr, there is a possibility of rearrangement. But I would say for this one, these are perfectly fine. There are better methods, and so the better methods would be to convert the OH to Cl, would be to use something like PCl3. Or another reagent is SOCl2. Or to go with PCl3, there's also PCl5. And then thionyl-chloride. So these reagents will convert the OH directly to the Cl. There is no carbocation rearrangement, so they go much faster. The big issue is when we try and convert a primary alcohol to the chloride, because we know we had to reflux it for 45 minutes in lab last semester to get that reaction to go. With something like PCl3, PCl5, you would go a little bit quicker. SOCl2, these reagents have a drawback as well. They're kind of air sensitive. When you use these, you've got to have something pull off the H plus that's formed. And so usually you use pyridine. And pyridine is a reproductive hazard for men, so we normally don't use that. And so there's all sorts of other issues. But for the most part, this will work smoother than HCl or HBr. But I don't know. If I'm not concerned too much about rearrangement, I'd use HCl and HBr. If it's primary, we should probably go with that. So the idea here is, if I want to form the least substituted double bond, I got to turn the OH into a halogen. And these are the ways to do it. And then if you had a chiral alcohol, then PCl3 either goes by inversion or retention of configuration. SOCl2, the same thing. If you used HCl, you would get a carbocation, so your chiral alcohol would now become 50-50 because you form a carbocation. So there's those little complications with stereochemistry. But the big issue is, if I want to do this reaction, I need to replace the OH with a halogen. Or a or a tosylate ester. And so the other way to do this is to react the OH group with a tosyl chloride. So this is abbreviated as a tosyl chloride. The tosyl is a paratoluene sulfonyl group. That's where the tosyl comes from. We'll learn later that this benzene ring with a methyl group on it is toluene, and then this is sulfonyl chloride. So it's, and the fact that they're 1,4 makes them para. So this is a para-toluene sulfonyl chloride. What happens is that you lose HCl in this process, and you end up adding the sulfur to the oxygen, and you end up forming then that, which is called, this is called the tosyl ester. And the beauty of the tosyl ester is it is a great leaving group. And not only is it a great leaving group, but I just turned my oxygen into part of that leaving group. So now I can make this entire group leave. And it's going to leave as an O minus S double bond O, and then the benzene ring. So this is a great leaving group, which means that it is a lousy base. Why is it a lousy base? Because it's very stable. Why is it very stable? Because it's got a lot of resonance structures. So tosylate esters are really good leaving groups. They're better than iodine. And so by using the tosyl chloride to make the tosylate ester, I've now made the oxygen of the OH part of the leaving group, so now I can substitute for what was an OH group that's now the tosylate ester. So all the things that I can do with this. So let me write that tosylate ester. And then we can think of all the different reactions I could do with this. Because now this whole thing right here is my great leaving group. So what can I do? I could treat this with NH2 minus. And if I treated it with NH2 minus, what kind of molecule am I going to form? Well, what kind of reactions does NH2 minus do? Or what does NH2 minus do? What's its job? It's going to be an E2 reaction because NH2 minus is a base. So it's going to come in and it's going to grab, now here's my alpha carbon, here's a beta carbon, here's a beta carbon. So which beta hydrogen is the NH2 minus going to grab? The one that's going to give you the most substituted double bond. So if I treated that molecule with NH2 minus, I'm going to get the most substituted double bond. And you might say, well, yeah, I could have gotten that by reacting the alcohol with sulfuric acid. Yeah, you could have. But that doesn't stop me from making, let's just be totally like Machiavellian out of this, you know. This is what you're going to have to do next week. So if I gave you that molecule and I gave you all these different reagents, you're going to have to write the products down here. So what else could I do? Tertiary oxide. What's the tertiary oxide going to do? It's going to do E2 and it's going to go after the beta hydrogen that is least sterically hindered. So that's going to form the double bond that is less substituted, the so-called Hoffman product. What else could I do? I could react this with Cl minus. What's that going to do? It's going to come in and, remember, this is now a really good leaving group. The Cl minus is going to come in and kick off the leaving group, which is tosylate. So now this one's going to do an SN2 reaction. These guys did E2s. This is going to do an SN2 reaction, and I'm going to form the Cl. If there was stereochemistry involved, since this is going to do an SN2, I'd end up with inversion of configuration. Okay. I like to throw this one in. What if I react this with NABH4? What am I going to do? What is NABH4? What is it a source of? H minus. So it is a source of H minus. What's the H minus going to do? Attack. It's going to do SN2. So it's going to come in, kick off the leaving group, and what am I going to make? Well, the molecule I just wrote. I'm going to kick the OH group off and make it an alkane. So really kind of the whole focus, although it's often tangents here and there, the whole focus of the stuff for today is I need to turn my OH into a leaving group. And I can do it by making it a halogen, or I can do it by making it a tosylate ester. Once I make it a tosylate ester, it's a leaving group. I can do E2s, I can do SN2s on it to kick it off. And then various methods to form the chlorides and the bromides with the SOCl2s and things, or use the tosylate ester and make the OH group into part of the leaving group with that. Let's make these problems. Let's make these homework problems for Monday. I wasn't necessarily going to do that, but I think I need to prompt you to get your reaction started, and I can answer questions about these. Hopefully I didn't release the answer key for this on Canvas. I'll check it when I go back to my office, but hopefully I didn't do that, or else you might get high scores on it. All right, if you have questions, email me or come and see me. There will be I think there's a video to watch for Monday, as well as a video and some lecture notes. And then on Wednesday of next week, we'll use that for review. So if you need to get one of these, come up front. Otherwise, I'll see you on Monday.